Functions and their graphs, part 2. They are very meaty sometimes in these pre-cal sections. Let's say, for instance, I have something like this. We'll say 3x minus 1. What this is actually a piecewise or a piece function. We'll graph it here in a minute. But first, let's just evaluate. If you wanted to evaluate, let's say 3, all you have to do is you're going to plug in this one when x is less than 5. You're going to plug in this expression when x is greater than or equal to 5. So if I want to find f of 3, since it's less than 5, you just plug it in. So 3 plus 2, 5. Let's say if I said f of 11. 11 is greater than or equal to 5, so I'm going to plug in 11. 33 minus 1, 32. Sure, they can get a little weird. Let's just throw some stuff out there. Let's say this one. Notice how, let's say we wanted to find f of 10. Well, is 10 less than negative 2 or greater than? Well, we know it's greater than, so that means plug in the bottom. Well, notice how it's constant. There is no variable for you to plug in. Well, if there's no variable for you to plug in, that just means no matter what, your answer is always the constant. Now let's say I said find f of negative 4. Negative 4 is less than negative 2, so that means I'm going to plug it in the top. Negative 4 squared minus 7. 16 minus 7. 9. So that's how you would evaluate certain points. Even though you can even have 3 equations or 3 expressions, it doesn't matter. Just look at the right hand side to see where it's going to be, and that is the one you plug in. You won't plug in both, but just the one that it fits. Now let's graph these. The best way that I can explain how to graph these is 5, like on this one. 5 is the pivotal point. 5 is the point where this graph is going to be, x plus 2 is going to be to the left of 5. This graph is going to be greater than or equal to 5, so it's going to be to the right of 5. It's not like this is an asymptote, but if you just wanted to kind of lightly do like a little line there just for you to know when it stops and starts, it is not an asymptote. But, like I said, it's going to tell you, oh, hey, this is where I stop. So you graph the line y equals x plus 2, just like you did in Algebra 1. You go up 2, slope of 1, rise 1, run 1. You're going to do your line like normal, but hey, stop when you get to 5. It's no line underneath, so it's going to be open. Well, now we do the second half, 3x minus 1. So again, graph it just like Algebra 1, 3x minus 1, so down 1, slope of 3, 1, 2, 3, over 1, and here's your graph. But the only thing is, we don't want it until it gets to the right of 5. So about right here, close dot because the line underneath. Now, I know this is obviously not to scale. The reason why I can say that is because if I were to plug in 5, I would get 15 minus 1 or 14. So this graph, this point should actually be up at 14. So I know this graph is not to scale. This one is a little bit closer. It actually should be about 7. So you can plug in the values in either one, and that will give you the exact point that you start and stop, and then you could do the slope. So that's another way you can do it. Let's say this one. Well, this one we've got -2 is where we're stopping and starting. So first, we're going to go down 7, and we're going to do a parabola. Now, the only thing is, ordinarily, it looks something like this. Well, we don't want it until it's less than -2 or equal to. So we'll say there, and that's what it would look like. But like I said, we don't care about all that. We only want it to the left of -2. And then this one, and notice how if you plug in -2, you get 4 minus 7, -3. That's pretty close. Yay me! That doesn't happen too often if I'm not trying to be exact. And this one at 8. Well, y equals 8. Don't let that throw you, because remember, that's just a horizontal line at 8. So you're going to go up 8, 2, 3, 4, 5, 6, 7, 8. At -2, open dot because no line. There you go. Now, it could be that you have 3 graphs. Oh, they do give you one with 3 graphs. So let's do it. Better get out a fresh sheet of paper. Let's see. Make sure. Whoop, yeah, I am a little off. Get back. We'll say, I don't know, maybe 2 if, and then maybe x squared when x is between -1 and 1, and then I don't know, maybe a line x plus 4. 1, sorry about that. So notice how this, we have 3 different sections. We've got -1, then we've got +1. So this is going to be all the way to the left. This one is going to be in the middle. This one's going to be to the right. And remember, notice how with each of them, we always start back at the origin when we graph it. So this one, y equals 2, horizontal line at 2. So 1, 2, but we only want it to the left of -1. There we go. Now then, in the middle, y equals x squared. And we want it between -1 and 1. Well, the good thing is we know it's just your nice little parabola. And notice how open circles because no line underneath. And notice how if you were to plug in -1, you get 1. So that's how you know it's exactly there. If you plug in +1, you also get 1. So that's why it's there. And then last, y equals x plus 4. So 1, 2, 3, 4. And at that point, rise 1, run 1. But we only want the graph, actually, I guess it'd be there to be more exact. We don't want to start it till here, but it is solid. There you go. I sometimes kid and call these Frankenstein graphs because you're piecing several together. Last but not least for this one, it's called the difference quotient. But what they don't tell you is actually, just to give you a little bit of heads up, if I put the limit as h goes to 0 out front, I could make it a calculus topic, and it would be the definition of derivative. But that's a couple of classes down the road, Math 125. So let's not worry about it yet. But I'm just saying they're being sneaky, and they're trying to prepare you for it. But they could give you something like y equals 7x and say, we want you to apply the difference quotient to it. Well, first, you're just going to plug in x plus h. So you're going to have 7 times x plus h minus f of x, which is just the original. So minus 7x all over h. Do a little bit of algebra, distribute 7x plus 7h minus 7x over h. And fun things happen. The original should always cancel. Then you're left with 7h over h, which is 7. And that's your answer. Let's even say it was y equals x squared plus 7x. Same thing. Everywhere, we'll even say a plus 3. Everywhere you see an x, first time you're going to put an x plus h. So that's going to be x plus h squared plus 7 times x plus h plus 3. This is where you're generally going to make your careless mistake. This is where you're going to have to do the FOIL method. Because remember, you can't just say x squared plus h squared. There's actually a 2xh in the middle. And you'll see that right here. Because when you FOIL, x squared plus xh plus xh plus h squared. Distribute here like normal, 7x plus 7h plus 3. Now, remember, that's just this part. Now, you want to subtract, and I'll just put it in parentheses like so. You want to subtract the original. So x squared plus 7x plus 3 all over h. So let's clean this up a little bit. We've got a x squared plus 2xh plus h squared. Then let's just bring that down. Now here's another spot where they'll get you, and you got to be super careful. Notice how it's a negative outside of the parentheses. So negative x squared minus 7x minus 3. And now, just like I told you, the original should always cancel. And so that leaves us with a 2xh plus h squared plus 7h all over h. So 2x plus h plus 7. There you go. So you have to watch for those. Of course, they could get a little weird. Most of the time, about as weird as they get, or at least in this book, is if there's a coefficient out front. If there is, after you FOIL right here, then you would distribute it to those terms and then do the rest of it. So like I said, if there was a coefficient, that's about as weird as they get. I know you're like, oh, that's weird enough. But they're not super hard, but you just got to be careful. Hope this was of help to you, and see you on the next section, 1.6.